In this video, I hope to capture the things about Rust's variables and assignment statements that catch people who are seasoned developers in other languages. Rust has a lot of really powerful capabilities, but we need to understand core functionality first. Because there are a lot of short topics, I've given you a table of contents so you can go right to what you need. We create a variable with the let statement. Rust will be happy to infer the variable's type from the value that you give it. Rust's numeric types are I for 2's complement integers, U for unsigned integers, or F for floating points followed by the number of bits you can get. F32 and F64 are IEEE 754 binary 32 and binary 64 floating point types. For these variables, Rust would infer that X is I32 and Y is F64. If you'd like to specify the type, you can do that with a colon. One variable can hold an ordered list of values called a tuple. It's like an array in that you access the variables by their positions. Quick sideline, that exclamation point means println is a macro. We'll talk about that more in a later video. For now, just believe it, and the first parameter is a format string. The values after that get evaluated and printed inside the curly brackets. As you can see, the values in a tuple do not have to be the same type. For this one, the compiler will infer int32, f64, and ampersand string, which is a string slice. More on that later too. We can use a technique called destructuring to get things out of a tuple. In this assignment statement, the tuple PQR gets matched with X, and the individual pieces of X are put into P, Q, and R. So this is what will be printed out. In other words, assignment statements are always pattern matching. The left-hand side gives a pattern of variables, and the right-hand side is matched against that pattern to make the assignments. I'll give more examples of that throughout this video. If you'd like to name the parts of that tuple, you can declare it as a struct. This declares a struct that holds three things: an integer, a real number, and a string. We can create a variable X to hold a struct and give values to each of those fields. Then we can use the name of the field to get the value back out. We can also use a destructuring assignment statement to get the value out. Look at this assignment. The pattern on the right is the player struct, with each field being a variable value. When that pattern is matched against X, the fields in X match, and the values in those fields go into the variables in the pattern. By default, variables are immutable. If we try to do this, we'll get a compile error. There are lots of good reasons to control mutability, but when you'd like it, you can have a variable mutable with the mute option. That'll compile with no problem. I like that it requires you to mark the variable as mutable, so you have to think about whether that mutability is really necessary. As we'll see, there are constructs that help us avoid mutability, and there are times when we explicitly want to control mutability. While Rust will infer types for it, it will not make any type conversions implicitly. Since infar is inferred to be an I32 and y is an F64, it will not allow us to assign y into infar without typecasting. We can force the conversion with an as clause, which will truncate y. And Rust is really thorough about these kinds of checks. I can't even divide y by 100 because that's an I32, and division is required that both operands be of the same type. So I have to use 100.0. In Rust, statements are instructions that perform an action and don't evaluate to anything. Expressions evaluate to a resulting value. For example, our let statements are statements. You can't store their value into a variable, which is different from languages like C and Ruby. However, Other than that, almost everything in Rust is an expression. Check this out. The curly brackets after the equals create a new scope block, and each scope block is an expression. In this one, we get input from a user and clean it up, and then we specify the value that the scope block should evaluate to. That's the value that will be stored into X. Another quick sideline. Notice I didn't need the parentheses around the condition in the if, and Rust requires that the then block have parentheses even if it's only one statement. So in Rust, we're always calculating something. Here, we're calculating the value of X, and to do that, we got input from a user. That function call is an expression that evaluates to an I32. And when we're finished with our calculation, we specify the result value without a semicolon. If we had put a semicolon here, we would have been telling the compiler that input was a statement, not an expression, and then the compiler wouldn't have known what to store into X. Since this feels new, let's do another example. In C or Java, we might have written this. Notice how that requires that we be able to change the value in X. In those languages, the compiler would have initialized it to 0. That mutability is a risk, and we can avoid it in Rust. This if statement is an expression. It will evaluate to either 1 or 13.3, and that value will be stored into X. Since X gets its value where it's declared, we don't need it to be mutable. And even though that if is an expression, we can embed other code into it too. This will still have the effect of storing either 1.0 or 13.3 into X. Again, we have to pay attention to two things. The last expression inside a scope block is the value that scope block will evaluate to, and it must not have a semicolon if we want it to be an expression. An enum in Rust is like enums in other languages in that it specifies an ordered list of discrete values. For example, I can make an enum for the weekdays, and I can use that enum like this. I think I'll do an entire video on the magic that comes from Rust's enums, but I'll give you one more example to show you how nice they can be. The unique thing about Rust enums is that you can attach data to each of the values, and the data that you attach can be different for each option. For example, suppose we're getting input from a user. We could define an enum for that like this. With this, we could know that the user pressed a left or a right arrow, and if they pressed an alphabetic key, we could store that letter that they typed. One enum that Rust gives us is the option enum. It has two values, some or none, and some can contain one piece of data. We often use this as a return value from a function. If something went wrong, or we can't do what the function is supposed to do, we return none. If things worked, we return some with the return value inside. For example, suppose we're building a 2D game and we want to move the player to the right. We'd build a function that takes the current X position and returns a new one after the move. However, if we're already at the right of the screen, we don't want to move, and we want the caller to know not to move the character. Let me explain this because we haven't seen some of this before. This line is declaring a constant named maxColumn that holds an integer value of 100. This is declaring a function named moveRight. It takes one parameter named x that is an I32, and it returns an option whose sum value can contain an I32. That scope block is the body of that function, and it is an expression that has to evaluate to the return value of the function. So, if x can move, it will return sum of x plus 1, and if x cannot move, it'll return none. Now that we have option, I can show you one more thing about the pattern matching of assignment statements. Suppose that I have moveResult. I'd like to get the value out of it. It feels like I could destructure it with something like this. Remember, the left-hand side of that equals is a pattern, and the right-hand side has to match. However, that pattern might not match. Move result might be none. Let's take a step back to explain. Remember this pattern that we used to destructure a tuple? That pattern will always match. So we call it irrefutable, and the compiler is quite happy to let us do that. However, with our option example, there's a chance that move result doesn't match sum of something because move result could be none. This makes the pattern refutable, and then you can't use it in a let statement because the compiler's afraid it won't know how to get the value that you're looking for. Instead, we have to use an if-let statement. The condition for this if is whether or not the pattern matched. If it did, the then block will be executed. And inside of the then block, I can use the value new x that we got from the destructuring of result. I can put an else on that if I want to, and that will be executed if the pattern doesn't match. So if our move result does not match sum of new x, we will beep because you can't move off the edge of the screen. If the not matching the pattern is fatal, the let else statement might work better. Again, this is a refutable pattern because it might not match. If it doesn't match, the stuff in the else block is executed, and that has to diverge, which means that we have to go somewhere other than the rest of the code. We can't keep executing after that because t will not have a value. If it does match t, the t gets matched and the scope of t continues beyond the end of the else block. Because of that need to diverge, this is usually only used for error handling. The last variable-related topic I want to talk to you about is shadowing of variables. If we have a variable with a given name and type, I can declare another one with the same name. It can have a different type and a different mutability. If I do that, the original one is technically still there, but I can't access it. Every time I use the name, it will reference the most recently declared value with that name. For example, here I have declared y to be of type f32, and then rounded it, and wanted it to be an integer. I couldn't use a simple assignment statement to store the rounded variable because that would require y to be mutable, and it would be a change in type. However, if I add a let to that assignment statement, everything works just fine. I've created a second y that is an immutable integer, and I can no longer see the first y. In some ways, this feels a little risky to me. What if someone did this by accident? I have some variable declared early in a function, and in the middle of that function, somebody accidentally declares a variable with the same name. The compiler will not complain unless the change in type causes my later references to not compile. However, just like in other languages, if we keep the scope of variables small and we name them well, this isn't too likely to happen. But still, why would we want to do this? Most often, it's a situation like my example. We're manipulating data, but the meaning of the data hasn't changed. For example, we could extend our cleaning up input example like this. This is making our input positive, and then rounding it to the hundredths position. The value is still our input, and by using shadowing, we don't have to create a bunch of variables with different names. My favorite example of when to use shadowing is making mutable variables immutable. In this scope block, I got an input from the user, and I stored it mutably. Then I did the cleaning up of that input, and the last line is an expression whose value the scope block will evaluate to. Then I shadowed input with an immutable input and stored the result in there. So while I was playing with it, I let it be mutable, but then I forced it to be immutable so the rest of the code can't play with it. those are my picks for cool things that Rust does with variables and assignment statements. Please let me know what you think, and if there are other Rust-specific topics you'd like me to talk about, let me know. Thanks, bye.